All right. We left off last time talking about these aldol addition reactions here. This is where we're going to pick up. All right, and what we're going to do first is we're going to do the full mechanism for these reactions. We picked some relatively simple aldehydes here. All right, I put down where we're going to start, which is our two aldehydes, and where we're going, our product of this reaction. All right. So step one of our mechanism here is you need to show me that enolate formation under basic conditions. All right, so everybody take a second. We have this base, sodium hydroxide. We can even get rid of the sodium, just the hydroxide here, boom. Okay, and we need that enolate formation here. So you're going to take one, not both of them, but just one of your aldehydes and show me how to form that enolate under basic conditions here. Once we do that formation, the next step is going to be nucleophilic attack. And the last step will be just a simple proton transfer. All right, so see if you can't take a second and give me our mechanism of these aldol addition reactions. All right, so first of all, that first step I said was enolate formation. What the heck do I mean by the enolate? So, just to remind you, where we started out was talking about by how ketones and aldehydes, they have this tautomerization to form these enols. And they're called enols because you have a double bond next to that alcohol group. Under basic conditions, though, these really good nucleophiles, these enolate ions form. And our enolate ion, kind of the same idea. We have an ene and an ol, but now we've deprotonated that oxygen to have that negative charge. But this thing is in resonance with another form here, where we have our carbanion on that alpha carbon. All right, either one of these would be considered your enolate ion. Either one of these could be used in your mechanism. But we said that this one over here on the right-hand side is a little bit easier to draw in terms of your mechanism. It'll just make it a little bit fewer arrows. Either one of these works. Again, they're both considered the enolate ion because they're in resonance with one another. So, first thing I need to do is just to simply deprotonate that alpha carbon. So I got a hydrogen on that alpha carbon. My base is going to come remove it. And this is going to form my enolate ion. All right, I'm going to copy and paste this second molecule down as well, because now we have our next step in our mechanism, our nucleophilic attack. Right, and this is kind of the key of these aldol reactions, is we have one molecule of our aldehyde that is going to act as the nucleophile at that alpha carbon. And we have another molecule of our aldehyde that is going to act as the electrophile, and which atom in here is going to be my electrophilic site? That carbonyl carbon, right? And so nucleophiles are going to do what nucleophiles do to an electrophile. It's going to attack. Whenever we have our carbonyl carbon get attacked, that kicks that pair of electrons up, forming that tetrahedral intermediate. All right, so I'll leave my dots in place here and show that now I have this new bond between my red and my blue carbon. All right, because that pair of electrons has jumped up onto that oxygen, now we have a negative charge. So then if the last step in this mechanism is just a proton transfer, I need to protonate that alkoxide ion. If we need an acid under basic conditions, we're just going to use water. And so that'll be my last proton transfer step. All right, and the important thing to note here, and when we're drawing our products, is it is the alpha carbon of one molecule. Oops, let me be consistent with my coloring. It is the alpha carbon of one molecule that has formed a new bond with the carbonyl carbon of its neighbor. All right, because that carbonyl carbon got attacked, it no longer is a carbonyl bond, a carbon-oxygen double bond, but now that's where my OH group is, right? That's now a carbon-oxygen single bond. Okay, so here's our aldol addition reaction here. Again, we need to form that good nucleophile, that enolate ion, by deprotonating that alpha carbon. That's then going to play the role of the nucleophile and attack one of its neighbors, whose carbonyl carbon is going to play the role of the electrophile. So now I got these two stuck together here. The last step is just simply to plug up that negative charge on that oxygen to protonate that oxygen in order to give me my aldol. Okay, cool. All right, let's, for the sake of practice here, you don't have to give me the full mechanism, but these ones are kind of tricky to draw here. So everybody just take a minute. If I take some 3-pentanone, and I add in some sodium hydroxide, give me my aldol addition product here. All right, so our aldol addition, importantly, we're going to have a new carbon-carbon bond, all right, between the alpha carbon of one of these ketones. So put this one right here. And the carbonyl carbon of its neighbor. All right, so I need to draw my new carbon-carbon bond between these things here. Okay, so I'm going to start by redrawing that nucleophile. All right, so there's my 3-pentanone with that alpha carbon colored in red here. And there's a new bond between that alpha carbon. And what's going to live on the other side of that new bond? The new bond between my alpha carbon and what? The carbonyl carbon of my other molecule. So if this is my new bond, what's on the other side must be that blue carbon, must be that carbonyl carbon of my neighboring molecule. All right, now I got to draw a bunch of other stuff on there, but I know that this carbon right here is that carbonyl carbon. Okay? Now, does my carbonyl oxygen stay a carbonyl oxygen? No, that would have way too many bonds, right? So I'm going to have attached to that, I got these 1, 2, 3 carbons going on, or rather 1, 2 on each side. But I also have that now OH group. My carbon-oxygen single bond. All right, so I think it's easiest to start by redrawing that nucleophile, because notice how my nucleophile I can see kind of just copy and pasted into my new molecule here. All right, those 5 carbons with my carbonyl group on carbon 3. But then for that alpha carbon, I've drawn this new bond in there. And again, what's on the other side of that bond must be that blue carbon, must be what was formerly my carbonyl carbon in my second molecule. So then I drew my 5 carbons about that carbonyl carbon. All right, and then the last step is what happens to that carbonyl oxygen. It goes from being a carbon-oxygen double bond to a carbon-oxygen single bond when that carbonyl carbon gets attacked. All right, so this is my aldol addition product here. Cool. All right, so we can also have what are called aldol condensation reactions. All right, and these are just when you do an aldol addition. But then you add in heat. All right, and when you heat this mixture, what that does is it causes a dehydration reaction. If we dehydrate an alcohol, what product do we get? What functional group do we get? An alkene, all right? So that's exactly what we're gonna see. We're gonna dehydrate this aldol addition product, and we're gonna get a carbon-carbon double bond when we lose that OH group. Okay, so let's just take this previous example here. Sort of get rid of all my little markings. All right, so here's my aldol addition product. All right, but now we're going to perform this dehydration reaction. All right, and just by looking at this reactant here, we could have one of 2 dehydration products depending on which way that double bond formed. Okay, we got 2 possible neighboring carbons. Well, more if you consider stereochemistry, but we'll ignore that for right now. All right, so we have 2 possible dehydration products. Why is that? Just simply because this alcohol has 2 neighboring carbons, which could potentially lose their hydrogens. All right, so the difference between these 2 products is where that double bond is. All right, now only one of these will actually form. All right, which one do we think? The top one or the bottom dehydration product? The bottom, cool. So I had a feeling everybody was going to get that part, but I'm worried that maybe we don't know why it would be the bottom one. All right, I have a feeling everybody's really tempted to say that it has to do with the degree of substitution. All right, and that is definitely a factor in determining the stability of an alkene. This bottom one is more stable. That is definitely why it's the major product. But there's something even more important than substitution that we see in that bottom product that we don't see at the top. All right, and I want you to rewind your minds back to the beginning of the semester. One of the very first things that we talked about were these special kind of dienes. And what was special about those dienes that we discussed? Conjugation, all right? So what is even more stabilizing than being a more substituted alkene is being a conjugated alkene. And we have on the bottom here a conjugated diene where those two double bonds, those two pi bonds, have that perfect spacing, okay? So you will always get the dehydration towards your carbonyl group here so that that alkene can be conjugated to that carbon-oxygen pi bond. All right, so it is not a substitution argument, it is a conjugation argument. All right, so let's just make note. This is what we call our aldol condensation product. Because we have these conjugated pi bonds. All right, your dehydration product will always have conjugated pi bonds in it. All right, rather your aldol condensation product. Okay, so to be clear, if we did this reaction here with NaOH, we would get our aldol addition product. If we did the exact same thing, but then we threw some heat in the mix, we would get that aldol condensation product. Did I just say the same thing twice? I don't know. Bottom line is if we just had NaOH, this would be our aldol addition. If we have NaOH plus heat, this will be our aldol condensation. All right, so the first step here in our aldol reactions is the formation of that enolate ion. And this reaction right here, it very much so favors, NaOH is not all that strong of a base. It very much so in equilibrium favors that aldehyde. Only a teeny tiny amount will actually be deprotonated, but again, like we said, that's enough. If 0.0001% of the population is an enolate ion, that's still going to go ahead and react and be a productive step forward towards the product side, right? So even if you only have a tiny population of reactive species, that's enough to kick this whole thing off, all right? Now, what about if we want to do what would be called a mixed aldol addition or condensation? All right, let's say I wanted to take something like acetone and then something like ethanol. All right, and I really want to get my aldol addition product. But specifically where acetone is the one playing the role of the nucleophile. And that ethanol is playing the role of the electrophile. Let's go for aldol condensations. We can practice that. All right. So, given if I tell you acetone is going to be the nucleophile and this ethanol, my aldehyde up here, is going to be the electrophile, everybody take a second and give me that aldol condensation product. All right, so I'm going to draw in that new bond between the alpha carbon of acetone and that carbonyl carbon of ethanol. All right, this would be the addition product. If I'm going to do the condensation product, I need to dehydrate this thing, get rid of that OH group, and replace it with a carbon-carbon double bond. Is this thing going to dehydrate to the left or to the right? To the left. All right, so that we get that conjugated double bond, this will be my condensation product. Okay? Now, before we go on, there's one little trick that I want you to show you about these aldol addition and condensation products that'll kind of help you do a little bit of a double check at the end to make sure that your product is correct. Okay? So, I don't know. Let's call this our double check. Okay, we're going to count from that carbonyl. All right, what I mean by that is starting at that carbonyl carbon, I'm going to count 1, 2, 3. And where is that new bond going to be located between carbons what and what? Between carbons 2 and 3, all right? And that is always going to be the case for these aldol addition and condensation products. If we want to go back up to our previous example, we can convince ourselves that if we start counting at that carbonyl carbon towards the other one, 1, 2, 3, where is that new bond? Again, between carbons 2 and 3, okay? So just a little quick double check, because I know our products are big and ugly here. If we count from our carbonyl carbon, we should find that new bond between carbons 2 and 3. All right, that's also where your new pi bond will be when you do your dehydration, when you do your condensation product. All right, so just kind of an easy double check. You should always have this 3 carbon spacing here where that new bond is between carbons 2 and 3. Cool, okay. I got a problem here. I can't just use that same strategy that we've been using of NaOH and heat, because there is absolutely no way for me to sort of mandate that the acetone would be the nucleophile and the ethanol will be the electrophile, right? If I just toss that into that mixture, I'm going to have some acetone reacting with the ethanol the way I want, but I'm also going to have the reversed. I'm going to have some ethanol playing the role of the nucleophile. I'm even going to have some acetone molecules reacting with one another and some ethanol molecules reacting with one another, right? It's going to be chaos in here. I'm going to get a mixture of a bunch of different products. So how do we do these mixed aldol addition or condensation reactions? This method won't work. We get a mixture of products. But don't worry, we got a solution here, all right? What we're going to do is we're going to take our nucleophile, or what we want to be our nucleophile. And the first thing we're going to do is treat it with what's called LDA. All right? LDA is a very strong base. It's also, we'll say, a very strong bulky base. So it's something that's a good base, but a terrible nucleophile. All right, and what that LDA is going to do, what that first step is going to do, is it's going to create that enolate ion exactly as we were doing in our first step before. But the difference is that it is a strong base, so strong that instead of this equilibrium favoring the ketone here, this reaction is going to go 100% to completion. We will convert every single one of those ketones into enolate ions. All right, so we're not worrying about that small population doing the work here. We're just saying we're going to take this whole thing and convert it all into enolate ions. And then in a second step, after we've done that, now we'll add in our electrophilic species, in this case, that ethanol. All right, now that we've added that in secondly, this just guarantees that the acetone will play the role of the nucleophile and the ethanol will play the role of the electrophile. In this particular case, because I was asking for the condensation product, we're also going to throw some heat in there. All right, and that will guarantee us our product. Okay, so let's kind of just make a note here for our aldol addition and our mixed aldol addition condensation. We're going to use LDA to convert one of our compounds to enolate, ensuring it is the nucleophile. Okay. By using LDA, we will take just acetone and introduce that LDA, and that guarantees that acetone is going to play the role of the nucleophile in this reaction, because 100% of those acetone molecules are converted into that nucleophile, that enolate form, right? Then we'll add in our electrophile and let them react together. Cool, so last thing we have to go over is a variation of these aldol addition reactions called a Claisen condensation. Even though it says it's a Claisen condensation, I'd just like to note that it's more analogous to an aldol addition reaction than it is an aldol condensation reaction. All right. A Claisen condensation is simply an aldol addition, but instead of using an aldehyde or ketone, we're going to use an ester. All right, we'll take a pretty simple ester here. All right, and what we're going to do is we're going to take this ester, and I'm just going to say base for right now. We'll talk about what base we use here in a minute. But notice that an ester, just like an aldehyde and a ketone, has an alpha carbon. And we know alpha carbons can play the role of what? Nucleophiles or electrophiles? Nucleophiles. And esters also have carbonyl carbons. And we know carbonyl carbons play the role of what? Nucleophiles or electrophiles? Electrophiles, right? So we're going to get the same game that we saw before, but starting with an ester instead of an aldehyde. Okay? So we're going to take two of these molecules here. One of them is going to be my nucleophilic alpha carbon. The other one's going to have my electrophilic carbonyl carbon. All right, and just like before, that base is going to deprotonate that alpha carbon. So I'm going to put a pair of electrons on that alpha carbon, which is what makes it a good nucleophile. All right, what's the next step going to be after I've made that good nucleophile alpha carbon? Nucleophilic attack. All right, cool. So everybody take a second. Draw me the product of this nucleophilic attack here. What's our intermediate for this reaction? right, so I redrew that nucleophile. I made that new bond so that I knew that on the other side of that new bond had to be that carbonyl carbon, right? That carbonyl carbon has a methyl group on one side, and then that, whatever, oxygen with its carbons on the other side, as well as now my oxygen that has that lone pair. We got a special name for these intermediates here. What do we call these? Because of their geometry. Tetrahedral. They went from being trigonal planar to tetrahedral. So we have our tetrahedral intermediate. All right, and we see these anytime a carbonyl carbon gets attacked. But now what we're going to start to do is we're going to get in the habit of looking at these tetrahedral intermediates, and we're going to ask ourselves, is there a leaving group? All right, if there were only carbons and hydrogens about that, then no. But here what we have and what we're going to see is this alkoxide ion here is going to play the role of a leaving group. All right? What's going to happen, and we're going to see this a lot with our tetrahedral intermediates. Everybody just look up here for a second. This pair of electrons on this oxygen is going to come back down and kick off that leaving group. All right? We saw this last class as well when we were talking about methyl ketones. They had that good leaving group, right? This oxygen is going to come back down and kick off that leaving group. Okay? So now I have this alkoxide ion that goes flying out of here. Everybody take a second and draw me my other product, what we would call our Claisen condensation product. All right, so let's just focus in on our Claisen condensation product here, okay? When that pair of electrons came back down on that oxygen, we reformed that carbon-oxygen double bond, right? Let's do our counting here. Again, if we start 1, 2, 3, where is our new bond located? Between carbons 2 and 3. So again, we can kind of use that same check to make sure that everything is spaced out the way that it should. Notice that instead of getting a carbonyl group and an alcohol group, I have 2 carbonyl groups, right? So this is the big difference between the products of a Claisen condensation versus an Aldol addition reaction. Okay? All right, same sort of idea. Let's talk about this thing for a second here, right? We said that this was our leaving group. But why? We kind of made like a big stink in that alcohols chapter about how those hydroxyl groups aren't good leaving groups, right? So why would all of a sudden we have this negatively charged oxygen playing the role of our leaving group here? Okay? Well, importantly, let's look at the previous step. What's unhappy about, like, why is this molecule here unhappy? What's giving it this high energy? the negative charge, right? I have my oxygen with a negative charge. Oxygen doesn't love to have a negative charge. We see it a lot, but it's still considered a high energy molecule, right? It's not like a chloride that's like more than happy to have a negative charge. It's a little pissed off here. But if we look at the previous step, what did we also have? An oxygen with a negative charge. So what's the difference in energy between these two steps? On the one hand, I have a pissed off oxygen. On the other hand, I have a pissed off oxygen, right? So there hasn't been an increase in energy between these two steps. And then we got to think about it from the standpoint of that other thermodynamic variable, the entropy standpoint here. I'm taking this big complicated molecule and I'm cracking it into these two smaller parts, which is always an entropically favorable event, right? So from an enthalpy standpoint, there's no change. Oxygen's mad on one side, oxygen's mad on the other side, right? But from an entropy standpoint, one of them is much more favorable. This thing is big and complicated. This is now broken into these two simpler parts. So yes, we do see oxygen playing the role of a leaving group, this negatively charged oxygen, which is something we don't see very often. But why is it allowed? Because again, in the previous step, we had the exact same thing, a negatively charged oxygen, and we have this entropically favorable splitting this molecule into two. All right, so the bottom line is we're going to see this thing play the role of our leaving group here. All right, and then last thing, within 1 second here, I said base. What should we use as our base? Well, notice that our leaving group is itself a very good base. So when we do these Claisen condensation reactions, we're really clever to use our leaving group as our base. And that way, when it gets kicked off, all we've done is replenish the supply of base in that mix, right? So your alkoxide ion, what you're going to use as your base is an alkoxide that matches that ester. All right, I had a 2-carbon tail on that ester. I'm going to use a 2-carbon alkoxide as my base in this reaction. Cool. Wonderful. All right, enjoy your weekend. We'll pick up on this stuff next time. No, just as long as you get through those questions. I can. You just have to send me kind of a good bit of heads up to like make sure I'm on there.
Okay, sounds good. Thank you.
Yep.
So, I'm planning to do the